Welcome to Deep Science Sleep. Close your eyes for a moment and imagine yourself floating peacefully in the vastness of space. You're drifting gently, weightless and serene, surrounded by the soft glow of distant stars. Below you, or perhaps beside you, direction loses its meaning here, hangs a beautiful sphere of silver white, its surface etched with ancient stories written in shadows and light. This is a moon, one of hundreds that waltz through our solar system in an eternal, graceful dance. As you float here in this quiet corner of the cosmos, you can feel the gentle pull of gravity, not harsh or demanding, but soft and reassuring, like an invisible thread connecting you to something vast and timeless. The silence here is profound, not empty but full of the patient movements of celestial bodies that have been performing their choreography for billions of years. Tonight, let these moons be your companions as you drift towards sleep, their stories unfolding in your mind like a lullaby sung by the universe itself. Our solar system is far more populated than you might imagine when you look up at the night sky. Beyond the 8 planets that orbit our sun, beyond the asteroids and comets and dust that fill the spaces between worlds, there exist hundreds upon hundreds of smaller worlds, satellites that circle their parent planets in an endless procession. As of early 2025, astronomers have confirmed the existence of at least 891 moons throughout our solar system, though the true number may be even higher. These celestial companions come in a staggering variety of sizes, shapes, compositions, and characteristics, each one a unique world with its own story to tell. Think about that number for a moment. 891 moons. It's a population that has grown dramatically over the years as our telescopes have become more powerful and our spacecraft have ventured farther into the outer reaches of our planetary neighborhood. Of these 891 confirmed moons, approximately 421 orbit the planets themselves, including the dwarf planet Pluto. The remaining 470 or so moons orbit other dwarf planets, asteroids, and trans-Neptunian objects, those distant, frozen worlds that exist in the twilight realm beyond Neptune's orbit, where sunlight is faint and temperatures plunge to nearly absolute zero. The diversity among these moons is truly breathtaking. Some are massive worlds, larger than the planet Mercury, with their own magnetic fields, substantial atmospheres, and complex geological processes. Others are tiny, irregular chunks of rock and ice, barely a few kilometers across, tumbling chaotically through space as they trace their elliptical paths around their parent bodies. Some moons are smooth and bright, their surfaces covered with fresh ice that reflects sunlight like a cosmic mirror. Others are dark and ancient, their faces scarred by billions of years of cosmic bombardment, telling the story of our solar system's violent early days. The very existence of these moons tells us something profound about the nature of gravity and the formation of planetary systems. When our solar system was young, about 4.5 billion years ago, it was a chaotic, violent place filled with colliding protoplanets, swirling disks of gas and dust, and tremendous gravitational forces that shaped the architecture we see today. Most planetary moons formed from the disks of gas and dust that circled the newly forming planets. Picture a miniature solar system in formation, with a young Jupiter or Saturn at its center and a flat disk of material spinning around it. Within that disk, particles began to stick together, gradually accumulating into larger and larger bodies through a process called accretion. Over millions of years, these growing clumps of material swept up more and more of the surrounding disk, eventually becoming the moons we observe today. But not all moons formed this way. Some, particularly the irregular moons of the giant planets, have a different origin story. These moons likely formed elsewhere in the solar system and were later captured by the gravitational influence of their current parent planet. You can often identify these captured moons by their peculiar orbits. Unlike the regular moons, which orbit close to their planet's equatorial plane in the same direction as the planet rotates, captured moons often have highly elliptical orbits, travel at extreme angles to their planet's equator, or even orbit in the opposite direction, what astronomers call a retrograde orbit. It's as if these moons are cosmic newcomers, forever marked by their outsider status, following paths that betray their foreign origins. The naming of moons is itself a peaceful and fascinating tradition that connects modern astronomy with ancient mythology and literature. Each moon discovered in the modern era initially receives a temporary designation, a combination of letters and numbers that indicates when and around which body it was discovered. For example, a moon discovered orbiting Saturn in 2009 might be designated S/2009 S1, where the S stands for Saturn. 2009 is the year of discovery, and S1 means it was the first Saturnian satellite discovered that year. Later, if the moon's orbit is confirmed and it proves to be a genuine, stable satellite, it receives an official name. Most moons in our solar system draw their names from mythology. The moons of Jupiter, for instance, are named after the lovers and favorites of the god Zeus from Greek mythology, Jupiter's Roman equivalent. Thus we have Europa, named for a Phoenician princess, Io, named for a priestess of Hera, Ganymede, named for a Trojan prince who became Zeus's cupbearer, and Callisto, named for a nymph who caught Zeus's attention. Saturn's moons also pull from mythology, though with a broader palette, drawing from titans and other figures associated with the mythological Saturn. More recently discovered Saturn moons have been named after giants from Norse mythology, expanding the cultural diversity of our cosmic naming traditions. Uranus stands unique among the planets in its naming convention. Rather than drawing from Greco-Roman mythology, Uranus's moons are named for characters from the works of William Shakespeare and Alexander Pope. Thus we have Oberon and Titania, the fairy king and queen from A Midsummer Night's Dream, Ariel and Umbriel, spirits from Pope's The Rape of the Lock, and Miranda from Shakespeare's The Tempest. This literary tradition gives the Uranian system a particularly whimsical and poetic character, as if the moons themselves are characters in a cosmic drama, each playing their role in the grand narrative of our solar system. The sheer number and diversity of moons raises a fascinating question. Why do some planets have many moons while others have few or none? Mercury and Venus, the two innermost planets, have no moons at all. Earth has just one, though as we'll discover, it's a particularly special one. Mars has two small moons. But once we move beyond the asteroid belt to the realm of the giant planets, the numbers explode. Jupiter has at least 95 known moons. Saturn boasts an incredible 274 confirmed moons, though the exact number becomes fuzzy because Saturn's rings contain countless small moonlets, and there's no clear boundary between a small moon and a large ring particle. Uranus has 28 known moons, and Neptune has 16. The reason for this dramatic difference lies partly in mass and partly in location. The giant planets, Jupiter, Saturn, Uranus, and Neptune, are massive enough that their gravitational influence extends far into space, allowing them to capture and hold on to many satellites. They also formed in regions of the solar system where there was abundant material from which moons could form. The inner solar system, by contrast, was a harsher environment. Higher temperatures meant that volatile materials like water ice couldn't easily condense, and the forming planets had less material from which to build extensive moon systems. The inner planets also experienced more violent collisions during the solar system's early days, collisions that might have knocked away any small moons they initially possessed. As you contemplate these hundreds of moons, orbiting silently in the darkness of space, there's something deeply calming about their persistence. These are worlds that have been following their appointed paths for billions of years, long before Earth had oceans, long before life emerged in those ancient seas, long before humans looked up and wondered about the lights in the sky. They'll continue their patient orbits long after we're gone, long after Earth itself has aged and changed beyond recognition. There's a kind of immortality in that constancy, a reminder that we're part of something vastly larger and more enduring than ourselves. Each moon is a time capsule, preserving clues about the conditions that existed when it formed. The cratered surfaces of ancient moons like Callisto tell us about the bombardment that all solar system bodies experienced billions of years ago. The smooth, young faces of moons like Europa and Enceladus speak of ongoing geological processes that continue to reshape these worlds. The exotic chemistry of Titan's atmosphere offers insights into the kinds of organic molecules that might have been present on the early Earth before life began. By studying moons, we're essentially reading the universe's own historical record, page by patient page. And there's something wonderfully egalitarian about moons. Unlike planets, which must meet specific criteria to earn that designation, must clear their orbits, must be massive enough to pull themselves into a spherical shape, moons come in all forms and configurations. Tiny, irregular chunks of captured asteroid coexist with massive, geologically active worlds. Ancient, unchanged surfaces spin beside moons that are constantly renewing themselves. In the democracy of celestial mechanics, all that matters is the patient tug of gravity, the endless orbital dance that connects satellite to planet to sun. So as you begin your journey towards sleep tonight, picture yourself as one of these cosmic wanderers, gently held in space by invisible forces, following your own peaceful orbit through the darkness. Let the knowledge of these 891 worlds, each with its own character and story, fill your mind with wonder rather than worry. They've been out there all along, these patient sentinels, spinning through the void, waiting for us to discover them, study them, and marvel at their quiet existence. In their company, your own concerns seem smaller, more manageable, more temporary. You are part of this vast, ancient dance, this cosmic ballet that began billions of years ago and will continue for billions more. Of all the moons in our solar system, there is one that holds a special place in human consciousness, one that has watched over our planet since the earliest days of our world's history. We call it simply the moon, sometimes Luna, from the Latin, and it has been humanity's companion since our species first looked up at the night sky with wondering eyes. Our moon's origin story is one of spectacular violence that led to enduring partnership. About 4.5 billion years ago, when Earth itself was barely 100 million years old, our young planet was still a molten world, still settling into its final form. The early solar system was a chaotic place, filled with protoplanets and planetary embryos, objects ranging in size from asteroids to Mars-sized worlds, all jostling for space, all bound by the gravitational influence of the young sun. In this cosmic game of billiards, collisions were inevitable. One day, though there were no days as we know them, no sun setting and rising on a recognizable horizon, a massive object struck the Earth. Scientists have named this impactor Theia, after the Titan goddess from Greek mythology who was the mother of Selene, the goddess of the moon. Theia was roughly the size of Mars, perhaps a tenth of Earth's mass, traveling at tremendous velocity. When it struck Earth, the impact released energy beyond comprehension, vaporizing both the outer layers of Earth and much of Theia itself. Imagine a collision so violent that it melts rock into vapor, so powerful that it sends enormous amounts of material blasting into space, forming a vast disk of molten and vaporized debris orbiting the shattered Earth. But from this destruction came creation. The debris disk began to cool, and as it did, particles started clumping together through that same process of accretion that formed the moons of the giant planets. Over time, perhaps just tens of millions of years, a blink of an eye in geological terms, this disk of debris coalesced into a single large body, our moon. The moon initially formed much closer to Earth than it is today, perhaps just 15,000 to 20,000 kilometers away compared to its current average distance of about 384,000 kilometers. From Earth's surface, it would have appeared immense, dominating the sky, looming overhead with a presence both beautiful and terrifying. The young moon was a molten world, its surface covered in an ocean of magma that glowed red-hot against the black sky. There was no atmosphere to diffuse that glow, so the moon's light would have been harsh and direct. Slowly, over millions of years, this magma ocean cooled. The denser materials, metals like iron, sank toward the moon's center, forming a small core. The lighter materials rose to the surface, creating the moon's crust. This process of differentiation gave the moon its layered structure, a solid inner core, a partially liquid outer core, a mantle, and a crust not unlike Earth itself, though on a much smaller scale. Today, the moon is a world of contrasts and quiet beauty. Its surface is covered in regolith, a fine dust created by billions of years of meteorite impacts. This dust is dark gray, almost charcoal in color, and it blankets the landscape like cosmic snow. The regolith can be several meters deep in places, and it has an unusual property. It's extremely fine and abrasive, clinging to anything it touches. The Apollo astronauts who walked on the moon found that the dust stuck to their spacesuits and equipment, and they carried its distinctive smell, described as similar to spent gunpowder, back into their lunar module. The moon's surface is marked by two distinct types of terrain. The bright highlands, or terrae, are the ancient, original crust of the moon, heavily cratered from billions of years of impacts. These regions are lighter in color because they're rich in a mineral called anorthosite, a type of rock that formed when the lunar magma ocean crystallized. The highlands are the oldest parts of the moon's surface, some areas dating back more than 4 billion years. Looking at the highlands is literally looking back in time to the solar system's violent youth. Then there are the Maria, Latin for seas, though they contain not a drop of water. The Maria are large, dark plains of basalt, formed by ancient volcanic eruptions that flooded low-lying areas and impact basins with molten rock. These lava flows occurred mostly between 3 and 4 billion years ago, during a period of intense volcanic activity on the young moon. The basalt that filled these basins is darker than the highland material, which is why the maria appear as dark patches when we view the moon from Earth. These dark and light areas create the familiar pattern we see, the face of the man in the moon, or the rabbit, or whatever pattern different cultures have imagined over the millennia. The moon's influence on Earth extends far beyond the visual beauty it provides in our night sky. Its gravitational pull plays a crucial role in making Earth the stable, habitable world we know. One of the moon's most important gifts to Earth is stabilization of our planet's axial tilt. Earth's rotational axis is tilted at about 23.5 degrees relative to its orbital plane around the Sun. This tilt is what gives us seasons. As Earth orbits the Sun, first one hemisphere and then the other leans toward our star, creating summer and winter, spring and fall. But without the moon, this axial tilt would not be stable. Computer simulations show that a moonless Earth would wobble chaotically, with its tilt varying wildly over relatively short periods, perhaps swinging from nearly 0 degrees to 85 degrees over the course of just millions of years. Such dramatic changes in axial tilt would create equally dramatic changes in climate. Seasons would become unpredictable. Regions that are temperate 1 millennium might become frozen wastelands or scorching deserts the next. The stability of Earth's climate over the past several billion years, stability that allowed life to evolve and diversify, owes a debt to the moon's gravitational influence, which acts like a stabilizing gyroscope, keeping Earth's tilt relatively constant. The moon's most visible effect on Earth is, of course, the tides. Twice each day, in most places on Earth, the ocean rises and falls in response to the moon's gravitational pull. This happens because gravity's strength decreases with distance, so the side of Earth closest to the moon feels a stronger pull than Earth's center, which in turn feels a stronger pull than the side farthest from the moon. This difference in gravitational force, what we call the tidal force, stretches Earth slightly, creating bulges in Earth's oceans. There are actually 2 tidal bulges on Earth. One forms on the side facing the moon, where the moon's gravity pulls the water more strongly. The other forms on the opposite side of Earth. This second bulge exists because Earth as a whole is falling toward the moon more than the water on the far side is being pulled, so the water on the far side gets left behind, creating a bulge. As Earth rotates beneath these 2 bulges, coastal regions experience 2 high tides and 2 low tides approximately every 24 hours and 50 minutes. The extra 50 minutes comes from the fact that the moon is also orbiting Earth, so Earth has to rotate a bit more than 1 full turn to bring a given location back into alignment with the moon. The tides do more than just move water up and down beaches. They affect ocean currents, which in turn influence global climate by transporting heat from the equator toward the poles. Tidal forces cause Earth's oceans to slosh against coastlines and ocean floors, creating friction that actually slows Earth's rotation. This means that Earth days are gradually getting longer, though very slowly, at about 1.7 milliseconds per century. At the same time as Earth's rotation slows, the moon is gradually moving away from Earth at a rate of about 3.8 centimeters per year. This happens because the tidal bulges on Earth don't point directly at the moon. Earth's rotation drags the bulges slightly ahead of the moon's position, and the gravitational pull of these offset bulges tugs on the moon, gradually accelerating it in its orbit. A faster orbit means the moon moves to a higher, more distant orbit, slowly spiraling away from Earth. This process has been going on for billions of years. When the Moon first formed, it orbited much closer to Earth, and Earth's day was only about 5 hours long. The tides back then would have been enormous, hundreds of times stronger than today's tides, with massive waves crashing against the primordial shores. Over billions of years, this tidal interaction has gradually slowed Earth's rotation and pushed the Moon farther away, creating the 24-hour day and the distant Moon we know today. This process will continue into the future. Eventually, in several billion years, Earth's rotation will slow enough that one side of Earth will always face the Moon, just as one side of the Moon always faces Earth today. At that point, the Moon will appear to hang motionless in the sky as seen from one hemisphere of Earth, while remaining forever invisible from the other hemisphere. The Moon's phases are another source of peaceful regularity in our lives. The Moon doesn't produce its own light. What we see is sunlight reflecting off the Moon's surface. As the Moon orbits Earth, the angle between the Sun, Moon, and Earth changes, causing us to see different portions of the illuminated half of the Moon. When the Moon is between Earth and the Sun, the side facing us is dark, and we have a new Moon. As the Moon continues in its orbit, we begin to see a thin crescent of light, which grows night by night into a first-quarter moon, when half the visible disk is illuminated. The illuminated portion continues to grow, waxing through the gibbous phase, until the Moon is on the opposite side of Earth from the Sun and we see its fully illuminated face, a full moon. Then the process reverses, the Moon wanes through gibbous and third quarter back to crescent and finally to new moon again. This entire cycle takes about 29.5 days, a period so regular that human cultures have used it as the basis for calendars since ancient times. There's something deeply soothing about the Moon's phases, the way they repeat with such reliability. No matter what chaos fills our daily lives, no matter what challenges we face, the Moon will continue its patient cycle, new to crescent to quarter to gibbous to full and back again. It's a cosmic metronome, marking time in a way that connects us to every human who has ever lived. Ancient farmers planned their crops by the Moon's phases. Medieval monks structured their prayers around the lunar cycle. Modern astronomers still use the Moon as a reference point for understanding celestial mechanics. In watching the Moon wax and wane, we're participating in an activity that spans the entire history of human civilization. The Moon's surface is marked by countless impact craters, scars from billions of years of collisions with asteroids and comets. Some of these craters are tiny, mere dimples in the regolith. Others are vast, hundreds of kilometers across, with raised rims and central peaks. One of the largest is the South Pole Aitken Basin, which spans about 2,500 kilometers in diameter and reaches depths of 8 kilometers below the surrounding terrain. This ancient impact basin, formed perhaps 4 billion years ago, is one of the largest and oldest impact structures in the solar system. Standing on its floor and looking up at its rim would be like standing at the bottom of a vast, bowl-shaped valley that stretches beyond the horizon in all directions. The lack of atmosphere and geological activity means that these craters remain largely unchanged over billions of years. On Earth, craters are quickly erased by erosion, tectonic activity, and volcanic resurfacing. But on the Moon, a crater formed 4 billion years ago looks much the same today as it did when it was fresh. The Moon is a museum of impacts, preserving a record of the bombardment that all inner solar system bodies experienced during their early history. By studying lunar craters, scientists can understand the rate and intensity of impacts over time, information that helps us understand Earth's own impact history, even though Earth's craters have been mostly erased by geological processes. Some of the moon's most interesting features are its rays, bright streaks of material that radiate outward from young impact craters. These rays are made of material ejected from the crater during the impact, material that was pulverized and melted by the force of the collision and then scattered across the lunar surface. The rays from young craters like Tycho and Copernicus can extend for hundreds or even thousands of kilometers, visible as bright streaks across the darker Maria and Highlands. Over time, these rays fade as the material is mixed with the surrounding regolith by subsequent smaller impacts, a process called space weathering. So bright, prominent rays are a sign that a crater is relatively young, perhaps only a few 100 million years old, while craters without visible rays are ancient, their rays long since faded into the background. The moon has no global magnetic field today, but some lunar rocks are magnetized, indicating that the moon once had a magnetic field in its distant past. This field was likely generated by motions in the moon's molten outer core, similar to how Earth's magnetic field is generated. The lunar magnetic field persisted for perhaps the first billion years of the moon's history, then gradually weakened and disappeared as the core cooled and convection ceased. Today, only remnant magnetism remains in certain rocks, particularly in the bright rays around young craters, where impact heating may have reset the magnetic signature. One of the most remarkable things about the moon is that it always shows the same face to Earth. This phenomenon, called tidal locking, occurs because the moon's rotation period, the time it takes to spin once on its axis, exactly matches its orbital period, the time it takes to orbit once around Earth. Both periods are about 27.3 days. This means that as the moon orbits Earth, it rotates at exactly the rate needed to keep the same hemisphere facing our planet. To an observer on the moon's near side, Earth would hang in one spot in the sky, slowly rotating but never rising or setting, a beautiful blue marble fixed in the blackness above. Tidal locking didn't happen by chance. It's the result of the same tidal forces that the moon exerts on Earth. Early in the moon's history, when it was still molten or partially molten, Earth's gravity raised tidal bulges on the moon, just as the moon raises tidal bulges on Earth. These bulges created friction within the moon's interior, which gradually slowed the moon's rotation. Over millions of years, this tidal friction slowed the moon's spin until its rotation period matched its orbital period, at which point the tidal forces no longer exerted a net torque, and the moon became tidally locked. This process of tidal locking is common in the solar system. Most large moons are tidally locked to their parent planets, always showing the same face to their primaries. The far side of the moon, which is often incorrectly called the dark side, remains hidden from Earth but is not perpetually dark. It receives just as much sunlight as the near side. It's simply the hemisphere we never see from Earth. The far side was a complete mystery until 1959, when the Soviet Luna 3 spacecraft flew around the moon and sent back the first photographs of this hidden hemisphere. What those images revealed was surprising. The far side looks significantly different from the near side. It has far fewer Maria, those dark volcanic plains, and is instead dominated by heavily cratered highlands. Scientists still debate why the two hemispheres are so different, but the leading theory involves the moon's crustal thickness. The crust is thicker on the far side, making it more difficult for magma to reach the surface and flood impact basins, which explains why the far side has fewer maria. The Apollo program, which landed 12 humans on the moon between 1969 and 1972, remains one of humanity's greatest achievements. The astronauts who walked on the lunar surface described it as a place of stark beauty, a landscape of grays and blacks under a pitch-black sky where stars shone without twinkling and the sun was a harsh, bright disk casting sharp shadows. There was no atmosphere to scatter light, so the sky was always black, even with the sun above the horizon. The horizon was closer than on Earth, appearing to curve down noticeably, because the moon is smaller. With surface gravity only 1/6 that of Earth, the astronauts could jump higher and had to learn a new way of moving, a kind of bounding, loping gait that looked almost like slow-motion ballet. The Apollo astronauts collected 382 kilograms of lunar rocks and soil, samples that scientists continue to study today. These rocks have told us the moon's age, revealed its volcanic history, and provided information about the composition of the lunar interior. Some lunar samples contain tiny glass beads, formed when molten rock from volcanic eruptions or impacts was thrown into the vacuum of space and cooled rapidly into perfect little spheres. Other samples show evidence of being shocked by impacts, their minerals transformed by the incredible pressures and temperatures generated in those collisions. Every lunar sample is a piece of history, a physical connection to processes that shaped our moon billions of years ago. As you drift towards sleep, imagine standing on the moon's surface, looking up at Earth hanging in the black sky. Earth would appear about 4 times larger than the moon appears from Earth, a brilliant blue and white marble swirled with clouds, the only spot of color in the entire black sky. You could see the continents and oceans, watch weather systems swirl across the face of your home world, see the Terminator line, the boundary between day and night, slowly sweep across the planet as it rotates. Every human who has ever lived, every story ever told, every triumph and tragedy, all of it contained on that blue sphere hanging above the airless plane where you stand. It would be a view of profound beauty and profound loneliness, a reminder of how precious and fragile our home is, and how vast and empty the space between worlds truly is. Now let us turn our attention outward from our own moon to other moons in the solar system, starting with one of the most intriguing worlds we've discovered, a moon that might harbor an ocean larger than all of Earth's oceans combined, hidden beneath a shell of ice. This is Europa, the 4th largest moon of Jupiter and one of the most promising places to search for life beyond Earth. Europa is slightly smaller than Earth's moon, with a diameter of about 3,100 kilometers compared to our moon's 3,474 kilometers. But while our moon is a dry, dead world, Europa is anything but. Its surface is covered in water ice, but not the pristine white ice you might imagine. Europa's ice has a slightly yellowish or brownish tint, likely caused by salts and minerals brought up from the ocean below and then irradiated by Jupiter's intense radiation environment. The overall effect is a surface that looks pale and strangely smooth, like a cracked eggshell or the surface of a frozen pond. And that comparison to a frozen pond is remarkably apt, because beneath Europa's icy shell lies a vast ocean of liquid water. Scientists estimate this ocean is about 60 to 150 kilometers deep, contained beneath an ice shell that might be 15 to 25 kilometers thick. To put that in perspective, the deepest parts of Earth's oceans reach about 11 kilometers deep. Europa's ocean is potentially 10 times deeper, and it likely contains 2 to 3 times more water than all of Earth's oceans combined. Think about that. This small moon, just a quarter of Earth's diameter, holds more water than our entire planet. How do we know this ocean exists? We've never drilled through Europa's ice or directly detected liquid water, but multiple lines of evidence point to its presence. First, there's Europa's density. Europa is less dense than it would be if it were solid rock and metal all the way through, suggesting it contains a significant amount of water or ice. Second, there's Europa's magnetic field behavior. Europa doesn't have its own magnetic field, but as it orbits through Jupiter's powerful magnetic field, the field induces electric currents in any electrically conductive layer within Europa. Spacecraft measurements have detected these induced currents, and the best explanation is that they're flowing through a salty, electrically conductive ocean beneath the ice. Third, there's the evidence written on Europa's surface itself. Europa has remarkably few impact craters, far fewer than you'd expect for a surface that's billions of years old. This suggests the surface is young, geologically speaking, perhaps only 20 to 180 million years old. Something is constantly renewing the surface, erasing old craters, and the most likely explanation is geological activity driven by the subsurface ocean. The ice shell is probably slowly convecting, with warmer ice rising from below and cooler ice sinking, gradually turning over and erasing old surface features. Europa's surface is covered with distinctive features that look like nothing else in the solar system. The most striking are the long linear features that crisscross the surface in complex, overlapping patterns. Some of these lines are ridges, raised above the surrounding terrain by hundreds of meters. Others are bands, wide swaths where the ice seems to have pulled apart and fresh ice has welled up from below. Still others are cycloids, graceful curves that trace arcing paths across the surface. These features likely form through a combination of tidal stress and ice shell dynamics. As Europa orbits Jupiter, tidal forces flex and stress the ice shell, creating cracks and faults that can extend for hundreds of kilometers. The patterns in Europa's lineae are remarkably complex. Some areas look like someone took a sheet of ice, broke it into pieces, and then shuffled the pieces around before freezing them back together. These chaotic terrain regions show clear evidence of disruption and movement, with ice blocks tilted, rotated, and displaced from their original positions. One popular model for how these forms suggests that warm ice or even liquid water rose up from below, melting the base of the ice shell and allowing the surface to break apart and raft around like icebergs before freezing back into place. It's like watching continental drift and seafloor spreading, but sped up and occurring on a much smaller scale. Europa's surface also shows evidence of cryovolcanism, volcanic activity involving water and ice rather than molten rock. Some features look like they might be cryovolcanic domes or flows, places where liquid water or slushy ice erupted onto the surface and then froze. More exciting are the hints of active plumes, geysers of water vapor erupting from Europa's surface. In 2012 and again in 2016, the Hubble Space Telescope detected what appeared to be plumes of water vapor rising up to 200 kilometers above Europa's south polar region. If these plumes are real and recurring, They would offer an incredible opportunity to sample Europa's ocean without having to drill through kilometers of ice. A spacecraft could simply fly through the plume and collect water droplets and ice particles for analysis. What keeps Europa's ocean liquid? After all, Jupiter's distance from the Sun means that sunlight is weak, only about 4% as strong as it is at Earth. The answer lies in tidal heating, one of the most important heat sources in the outer solar system. Europa orbits Jupiter in a slightly elliptical orbit, and it's in an orbital resonance with two other Jovian moons, Io and Ganymede. For every orbit Ganymede makes around Jupiter, Europa makes exactly 2 orbits, and Io makes exactly 4. This 4-2-1 resonance keeps Europa's orbit from becoming perfectly circular. As Europa moves closer to and farther from Jupiter during each orbit, Jupiter's enormous gravitational pull stretches and squeezes Europa's interior. This constant flexing generates friction, and friction generates heat, enough heat to keep Europa's subsurface ocean liquid despite the Moon being so far from the Sun. The same tidal heating that keeps the ocean liquid also drives geological activity on Europa's surface. The energy flowing through Europa's interior, perhaps 100 times more than the energy Earth receives from radioactive decay of elements in its interior, powers the processes that resurface the ice shell, drive cryovolcanism, and might even power hydrothermal vents on the ocean floor, similar to the vents we find at the bottom of Earth's oceans. And this is where Europa becomes truly exciting as a potential abode for life. On Earth, we've discovered thriving ecosystems around deep-sea hydrothermal vents, places where hot, mineral-rich water erupts from the ocean floor. These ecosystems don't depend on sunlight. Instead, they're based on chemosynthesis, a process where microorganisms extract energy from chemical reactions involving the minerals and compounds in the vent fluids. These microorganisms form the base of a food chain that includes larger organisms like tube worms, shrimp, and crabs, all living in complete darkness kilometers below the ocean surface. If Europa has similar vents on its ocean floor, and if those vents provide similar chemical energy sources, there's no fundamental reason why life couldn't exist there too. Europa's ocean has liquid water, it has energy from tidal heating, and it likely has the chemical building blocks necessary for life. Water circulating through Europa's rocky interior would dissolve minerals and create a rich chemical environment. The ocean probably has a salinity similar to Earth's oceans, based on the colors we see on Europa's surface and the way Europa interacts with Jupiter's magnetic field. It might even have a chemical composition similar to certain parts of Earth's oceans. Of course, we don't know if life actually exists on Europa. The ocean might be there with all the right ingredients, but life might never have emerged. Or life might have started but then died out. Or conditions might be subtly different from Earth in ways that make life impossible. But the possibility is tantalizing enough that NASA and the European Space Agency are planning missions to investigate. NASA's Europa Clipper mission, scheduled to arrive at Jupiter in 2030, will make multiple close flybys of Europa, mapping its ice shell, characterizing its ocean, studying its geological activity, and searching for plumes. The European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, will also study Europa as part of a broader investigation of Jupiter's icy moons. Looking at images of Europa, you see a world that is both alien and strangely familiar. The ice shell, crisscrossed with cracks and ridges, looks like something you might see on a frozen lake after a winter of freezing and thawing, refreezing and breaking. The reddish-brown streaks look almost like rust stains or mineral deposits. The chaotic terrain looks like ice flows jumbled together. It's a landscape that speaks to processes we can understand, even if the scale and the details are foreign. There's something peaceful about that, the idea that even in the outer solar system, on a moon orbiting a giant planet hundreds of millions of kilometers from the sun, the same basic physics and chemistry that govern Earth are at work, creating landscapes and driving processes that would be at least somewhat recognizable. Imagine diving beneath Europa's ice shell, descending through kilometers of ice that transition from solid near the surface to slushy and finally to liquid water. The ice above filters out what little sunlight reaches Europa, so the ocean below is utterly dark, darker than the deepest parts of Earth's oceans, but perhaps not entirely featureless. If there are hydrothermal vents, they might glow with a dim red light from the heat. Bioluminescent organisms, if they exist, might provide their own illumination, just as many deep-sea creatures on Earth do. Currents would flow through this ocean, driven by tidal heating and the rotation of Europa, creating zones of circulation and mixing. The seafloor would be rocky, the actual solid surface of Europa, covered perhaps in mineral precipitates from the hydrothermal systems. It would be a world within a world, an entire ocean ecosystem hidden from view, waiting to be explored. Europa reminds us that habitability doesn't require Earth-like conditions. You don't need a planet. You don't need sunlight. You don't even need to be in the traditional habitable zone, that region around a star where temperatures allow liquid water on a planet's surface. All you need is liquid water, a source of energy, and the right chemical ingredients. Europa has all three, hidden beneath its icy exterior, a secret ocean that might be one of the most important discoveries in human history if it turns out to harbor life. As you continue your descent into sleep, let yourself imagine floating in Europa's dark ocean, suspended in water that has been liquid for billions of years, insulated from the vacuum of space by kilometers of protective ice. It's a place of profound stillness, profound darkness, and profound possibility. A place where life might exist in forms we can't yet imagine, adapted to an environment unlike anything on Earth. A place that reminds us that the universe is full of surprises, that worlds we once thought were dead and frozen might actually be dynamic, active, and perhaps even alive. Let us journey now to another extraordinary moon, one that in many ways is even more alien than Europa, even though it too might harbor an ocean beneath its surface. This is Titan, Saturn's largest moon and the second largest moon in the entire solar system, a world shrouded in a thick, orange atmosphere that hides its surface from view. Titan is larger than the planet Mercury, with a diameter of 5,150 kilometers. It's the only moon in the solar system with a substantial atmosphere, indeed the only solar system body besides Earth with a thick nitrogen atmosphere. Titan's atmosphere is about 1.5 times thicker than Earth's, with a surface pressure of about 1.5 bar compared to Earth's 1 bar. Standing on Titan's surface, you would feel slightly more atmospheric pressure than you experience at sea level on Earth, though you certainly couldn't breathe it. The atmosphere is about 95% nitrogen and about 5% methane, with traces of other hydrocarbons and organic compounds. This thick atmosphere gives Titan its distinctive appearance. From space, Titan looks like a featureless orange sphere, its surface completely obscured by layers of hydrocarbon haze. The orange color comes from complex organic molecules called tholins, created when methane high in the atmosphere is broken apart by ultraviolet light from the sun, and the molecules recombine into more complex forms. These tholins form a thick smog layer that envelopes the entire moon, scattering light and giving Titan its characteristic glow. It's beautiful in its own way, this globe of orange haze floating in space, but it's also frustrating if you want to see what's beneath. That frustration drove NASA to develop special radar systems for the Cassini spacecraft, which orbited Saturn from 2004 to 2017, and to equip the Huygens probe, which descended through Titan's atmosphere to land on the surface in 2005. What these missions revealed was astonishing. Beneath the haze, Titan has a landscape that looks remarkably Earth-like, at least in terms of the types of features present, even though the details are utterly alien. Titan has lakes and seas, but not of water. These are lakes and seas of liquid methane and ethane, hydrocarbons that exist as gases on Earth but which are cold enough on Titan to condense into liquids. Titan's surface temperature is about -179 degrees Celsius, cold enough that water ice is as hard as rock, and methane behaves the way water does on Earth. Titan's largest sea, Kraken Mare, is bigger than the Caspian Sea on Earth, covering an area of about 400,000 square kilometers and reaching depths that might exceed 300 meters. Ligeia Mare, the second largest sea, covers about 126,000 square kilometers. These seas are located primarily in Titan's North Polar region, while smaller lakes are scattered across the northern latitudes. But the South Pole has fewer lakes, a mystery that scientists are still working to understand. One theory suggests that Titan, like Earth, experiences seasons, but on a much longer timescale. A Saturnian year is about 29.5 Earth years, so each Titan season lasts more than 7 Earth years. The distribution of lakes might change over time as methane evaporates from one polar region and precipitates in the other, following a seasonal cycle that spans decades. Titan has clouds, but again, not water clouds. These are clouds of methane, which occasionally produce methane rain. Cassini observed clouds moving across Titan's atmosphere and even detected what appeared to be rainstorms, events where methane precipitation darkened the surface in certain areas. This methane rain doesn't fall as gentle drizzle. Titan's thick atmosphere and low gravity, about 14% of Earth's, mean that raindrops can grow quite large, perhaps up to a centimeter in diameter, and they fall slowly, taking several hours to descend from cloud to surface. Imagine standing on Titan during a rainstorm, watching huge droplets of liquid methane drifting down from the orange sky, splashing onto the surface around you, the impacts happening in what would seem like slow motion compared to rain on Earth. Titan has rivers and drainage channels, carved by methane rain running off highlands and flowing toward the lakes and seas. Cassini's radar mapped these channels in detail, showing branching networks that look exactly like river systems on Earth. The rivers are mostly dry, suggesting that methane rain is sporadic, but when it does rain, these channels fill and carry liquid methane toward the lakes. Some channels show evidence of meanders, those graceful curves that rivers on Earth develop as they erode their banks and shift course over time. The physics of fluid flow are universal, so methane rivers on Titan behave similarly to water rivers on Earth, even though the fluid is different and the temperature is vastly colder. Titan even has something resembling Earth's water cycle, except it's a methane cycle. Methane evaporates from the lakes and seas, rising into the atmosphere where it condenses into clouds. The clouds produce methane rain, which falls back to the surface, runs off through river channels, and eventually makes its way back to the lakes and seas. This is the only other place in the solar system where we see this kind of active liquid cycle on the surface, this exchange between surface reservoirs, atmosphere, and back to surface. It makes Titan eerily familiar despite being completely alien. The surface of Titan is diverse, showing features that speak to multiple geological processes. There are vast plains, probably covered in layers of organic sediment that have settled out of the atmosphere over billions of years. There are dune fields, regions where wind has sculpted the surface into long, linear dunes that can stretch for hundreds of kilometers. These dunes are made not of sand grains of silicate minerals like Earth's sand dunes, but of grains of hydrocarbon material, possibly tholins that have rained out of the atmosphere or solid methane and ethane. The dunes are shaped by winds that blow primarily from west to east, creating parallel ridges that can be over 100 meters tall. Titan also has mountains, though not the kind formed by tectonic activity. Titan's crust is water ice, and at Titan's frigid temperatures, water ice behaves like rock. Titan's mountains are essentially ice mountains, uplifted blocks of frozen water. The tallest peaks reach about 3,300 meters high, substantial by Titan standards though modest compared to the highest mountains on Earth or Mars. Most intriguingly, Titan shows evidence of cryovolcanism, volcanic activity involving not molten rock but liquid water or water ammonia slurries erupting from the interior. Some features seen by Cassini look like they could be cryovolcanic flows or domes, places where liquid water welled up from below and then froze on the cold surface. One feature, Sotrapatera, looks particularly promising as a cryovolcanic site, with what appears to be a caldera-like depression and associated flows. If cryovolcanoes exist on Titan, they would provide a way for material from Titan's interior to reach the surface, potentially bringing up organic molecules from the subsurface ocean that might exist deep within Titan. And yes, despite its surface being home to liquid methane, Titan likely has a subsurface ocean of liquid water, just like Europa. Evidence for this ocean comes from measurements of Titan's shape and gravitational field made by Cassini. These measurements suggest that Titan's interior is partially liquid, with a water ocean perhaps 50 to 100 kilometers below the surface ice crust. This ocean would be quite different from Europa's, probably containing dissolved ammonia which acts as antifreeze, lowering the freezing point of water and allowing the ocean to remain liquid even at temperatures well below 0 Celsius. The combination of a subsurface water ocean and a surface covered in organic molecules makes Titan another candidate in the search for life beyond Earth. The surface lakes and seas are probably too cold and too chemically inhospitable for life as we know it, but the subsurface ocean might offer a more hospitable environment. And even if the ocean itself is too isolated from the surface to support life, some scientists speculate about the possibility of exotic life forms that could exist in the surface methane lakes. Life based on chemistry we can barely imagine, using liquid methane as a solvent instead of water and metabolizing in ways completely unlike terrestrial life. The Huygens probe's descent to Titan's surface in 2005 provided our only direct look at conditions near and on the surface. As Huygens descended, it took photographs showing a landscape of highlands and drainage channels, looking remarkably like aerial views of desert regions on Earth. The probe landed in a flat plain, and the images from the surface showed a landscape littered with rounded pebbles and rocks. Water ice rounded by erosion from liquid methane. The sky was a dim orange, with visibility extending to the horizon but illumination only about 1/1000th as bright as daylight on Earth. The sun was hidden behind layers of haze, providing only a diffuse glow. Huygens measured the surface temperature at -179.4 degrees Celsius, cold enough to freeze methane but warm enough for methane to evaporate over time. The probe also detected methane vapor near the surface, suggesting that the landing site was slightly moist with liquid methane, perhaps like a damp streambed after a rain. The surface had a consistency something like wet sand, offering some resistance but yielding under pressure. Huygens operated for only about 90 minutes on the surface before its batteries died. But those 90 minutes gave us our only ground-level view of any world in the outer solar system. One of the most remarkable things about Titan is that despite being nearly 10 times farther from the Sun than Earth, despite receiving only about 1% of the sunlight Earth receives, it has active geology, a dynamic atmosphere, and weather. Most worlds at that distance are frozen, geologically dead, their surfaces unchanged for billions of years except for the slow accumulation of impact craters. But Titan is alive in the geological sense. Its surface is being constantly modified by wind, by methane rain, by deposition of organic materials from the atmosphere, and possibly by cryovolcanism. It's a world where processes we understand from Earth are happening, but with alien materials and at alien temperatures. The thick atmosphere also means that Titan has climate, something most moons lack. There are atmospheric circulation patterns, with rising air near the equator, sinking air at the poles, and winds blowing from high pressure to low pressure regions. There are seasons, driven by Titan's tilt and its orbit around Saturn. There might even be something analogous to El Niño events on Earth, periodic changes in atmospheric and surface conditions driven by feedback between the atmosphere and the methane lakes. Looking at Titan, you can't help but think of it as a frozen version of early Earth. The chemistry happening in Titan's atmosphere, this constant production of complex organic molecules from simpler starting materials, might be similar to the chemistry that occurred on the early Earth before life began. By studying Titan, we might be learning about the kinds of organic chemistry that led to the origin of life on our own planet. Titan is like a natural laboratory, a place where we can observe these processes in action, frozen in time because of the cold temperatures that slow down all chemical reactions. There's something profoundly peaceful about imagining Titan, this distant moon orbiting slowly around Saturn, its thick atmosphere protecting it from the harshness of space, its lakes quietly evaporating and refilling over decades-long seasons, its rivers flowing occasionally when methane rain falls from the orange sky. It's a world where change happens, but slowly, gently, following rhythms measured in Saturnian years. It's a world that has been doing its own thing for billions of years, will continue for billions more, patient and persistent in its alien way. As you drift deeper into sleep, let Titan's orange glow fill your vision. Imagine standing on its surface, looking up through the thick haze at the dim sun, feeling the slight weight of the dense atmosphere pressing gently on your body. Around you, the landscape stretches away in shades of brown and orange, rocks of water ice scattered across organic sediments, drainage channels cutting through the plains, perhaps the shore of a methane lake visible in the distance, its surface smooth and mirror-like under the hazy sky. It's a place of profound strangeness and profound tranquility, a world unlike any other, quietly existing in the outer reaches of our solar system. From the murky depths beneath Europa's ice and the orange haze of Titan, let us turn to a moon of spectacular, crystalline beauty, a world that sparkles like a cosmic jewel in the sunlight. This is Enceladus, another of Saturn's moons, smaller than Europa and far smaller than Titan, but no less fascinating and perhaps even more likely to harbor life. Enceladus is a small moon, just 504 kilometers in diameter, about the width of the state of Arizona. You could drive across Enceladus in a few hours if there were roads. But what Enceladus lacks in size, it more than makes up for in surprises. Its surface is covered in almost pure water ice, making it the most reflective body in the solar system. Enceladus reflects about 90% of the sunlight that hits it, compared to about 40% for Europa and 12% for our own moon. From a distance, Enceladus looks like a tiny, brilliant white star, gleaming against the blackness of space. The high reflectivity isn't just aesthetically pleasing, it tells us something important. A bright, reflective surface means the ice is fresh, not darkened by radiation damage or contamination with rocky material. And fresh ice means recent geological activity, something refreshing and renewing the surface. For decades, scientists wondered what could be keeping such a small moon geologically active. Small bodies cool quickly, losing their internal heat to space, and should become geologically dead within a few 100 million years of their formation. Yet Enceladus was clearly active, much more active than its size would suggest. The answer came in 2005, when the Cassini spacecraft made a close flyby of Enceladus and discovered something spectacular. Enormous geysers of water vapor and ice particles were erupting from Enceladus's south polar region, jetting hundreds of kilometers into space. These plumes were so large and dense that Cassini could fly through them and sample their composition directly. The discovery was stunning. Here was a moon barely 500 kilometers across, so small you could hold a reasonably scaled globe of it in your hands, shooting water into space like some kind of cosmic fountain. The source of these geysers turned out to be a set of 4 parallel fissures near the South Pole, features that scientists nicknamed the tiger stripes because of their appearance. These fissures, officially named Damascus, Baghdad, Cairo, and Alexandria Sulci, are about 130 kilometers long, 2 kilometers wide, and cut into ridges that rise about 100 meters above the surrounding terrain. The stripes appear blue-green in enhanced color images, darker than the surrounding ice, suggesting they're coated with larger ice grains or possibly with organic material or other contaminants from Enceladus's interior. But the most remarkable thing about the tiger stripes is their temperature. While most of Enceladus's surface hovers around -201 degrees Celsius, the tiger stripes are much warmer, reaching temperatures as high as -121 degrees Celsius in the hottest spots. That's still incredibly cold by Earth standards, cold enough to freeze carbon dioxide, but it's 80 degrees warmer than the surrounding terrain, an enormous difference. Infrared observations show that these fissures are radiating about 15 gigawatts of heat, far more heat than such a small moon should be able to generate through radioactive decay alone. The explanation for this heat and for the geysers is tidal heating, the same process that keeps Europa's ocean liquid. Enceladus orbits Saturn in a 2-to-1 resonance with the moon Dione. For every 2 orbits Enceladus makes, Dione makes exactly one. This resonance keeps Enceladus's orbit slightly elliptical, causing it to move closer to and farther from Saturn during each orbit. As with Europa, this changing distance means varying tidal forces, which flex Enceladus's interior, generating friction and heat. The heat is somehow concentrated at the South Pole, possibly because of the way the fissures open and close as Enceladus moves through its orbit, pumping heat through the cracks. Cassini made multiple flybys of Enceladus over the years, passing through the plumes and analyzing their composition. What scientists found was remarkable. The plumes contain water vapor, of course, but also ice particles, carbon dioxide, methane, ammonia, and simple organic molecules like formaldehyde and acetylene. More importantly, the plumes contain salts, specifically sodium chloride, common table salt, and potassium salts. The presence of salts is significant because it indicates the water in the plumes comes from a salty liquid ocean, not just from melting ice. When salty water is ejected into space and freezes, the salts get incorporated into the ice particles, and that's exactly what Cassini detected. The plumes also contain molecular hydrogen, a discovery announced in 2017 that excited astrobiologists tremendously. Molecular hydrogen is significant because it can serve as a chemical energy source for life. On Earth, certain microorganisms called methanogens live in environments where oxygen is absent. They get energy by combining hydrogen with carbon dioxide to produce methane, a process called methanogenesis. The presence of hydrogen in Enceladus's plumes suggests that water from the ocean is reacting with rock in Enceladus's interior, a process called serpentinization that produces hydrogen. This means Enceladus has all three ingredients necessary for life as we know it: liquid water, organic molecules, and an energy source. Based on all this evidence, scientists now believe that Enceladus has a global ocean of liquid water beneath its ice shell, most likely 30 to 40 kilometers beneath the surface over most of the Moon, but only a few kilometers beneath the tiger stripes where the shell is thinnest. This ocean is in direct contact with Enceladus's rocky core, allowing water to react with the rock and dissolve minerals. The ocean is probably about 10 kilometers deep, extending all the way around the Moon beneath the ice. The geysers offer an unprecedented opportunity. When scientists talk about searching for life on Europa or Titan, they usually discuss missions that would land on the surface and drill through kilometers of ice, technically challenging and expensive propositions. But with Enceladus, we don't need to drill. The Moon is bringing samples of its ocean directly to us, launching them into space where a spacecraft could collect them. A future mission could fly through the plumes with more sophisticated instruments than Cassini had, specifically designed to detect biosignatures, chemical or molecular evidence of life. We could search for amino acids, the building blocks of proteins, or for lipids, the molecules that make up cell membranes, or even for intact cells if they exist and survive the journey from ocean to space. The surface of Enceladus outside the South Polar region is relatively crater-free and crisscrossed with fractures and ridges. Different regions show different ages based on crater density. Some areas look ancient, while others look geologically young, perhaps only a few million years old. This suggests that Enceladus's geological activity waxes and wanes over time, perhaps driven by changes in orbital eccentricity as Enceladus and Dion's orbital resonance shifts slightly. During periods of higher eccentricity, tidal heating would be stronger, leading to more geological activity and more rapid resurfacing. During periods of lower eccentricity, activity would decline and craters would accumulate. One particularly striking feature on Enceladus is a region near the North Pole covered with fractures that create a pattern nicknamed the chevron terrain. These fractures are straight and parallel, cutting across the surface in sets oriented in different directions, creating a cross-hatched appearance. They might be ancient tiger stripes, formed long ago when Enceladus's south pole was in a different location. Enceladus might have undergone a reorientation at some point in its past, with the entire moon rolling over so that what used to be a pole ended up at the equator and vice versa. Such reorientations can happen if a heavy mass inside a moon shifts position, causing the moon to rebalance itself. The geysers themselves are a sight to behold. Cassini images show them as delicate streamers of ice and vapor, arcing gracefully away from Enceladus's south pole and spreading out into space. The larger particles, being heavier, fall back to the surface, particularly in the south polar region, where they create a fresh coating of ice. The smaller particles and vapor escape Enceladus's weak gravity, about 1% of Earth's, and spread out along Enceladus's orbit. This material gradually disperses throughout the Saturnian system, some of it eventually falling onto Saturn itself, but much of it forming Saturn's E-ring, a faint, diffuse ring that extends from about 180,000 kilometers to about 480,000 kilometers from Saturn's center. Enceladus orbits right in the middle of the E-ring at about 238,000 kilometers, and its geysers are the source of all the E-ring's material. The E-ring is faint and difficult to see from Earth, but in the right lighting, from the right angle, it glows softly, backlit by the sun, a vast halo of ice surrounding Saturn, all of it ultimately originating from the geysers of tiny Enceladus. There's something almost magical about Enceladus, this tiny moon glowing brilliant white, its south pole decorated with mysterious blue-green stripes, water geysers erupting from fissures in the ice, spraying ocean water into space where it freezes into tiny particles that catch the sunlight and create a ring around Saturn. It's a moon that punches way above its weight class, a small world doing big things, reminding us that size doesn't necessarily determine importance or interest. Imagine standing on Enceladus's south polar region, perhaps near one of the tiger stripes. The gravity is so weak that you weigh only about 1% of your Earth weight. You could jump many meters into the air with ease. The surface beneath your feet is water ice, slightly soft in places where the heat from below has warmed it. A short distance away, one of the fissures cuts across the landscape, a crack in the ice perhaps a kilometer or two wide. From within the crack, a geyser erupts, a jet of water vapor and ice crystals shooting skyward at hundreds of meters per second. The geyser is so powerful that the material escapes Enceladus entirely, and you can see the trail of ice particles stretching up and away, thinning as they spread, eventually disappearing into the blackness. The sun hangs in the black sky, small and distant, but bright enough to make the ice around you glow. And looming overhead, taking up a huge swath of sky, is Saturn itself, a vast oblate sphere with its glorious rings, all of it slowly moving across the sky as Enceladus orbits. It would be a scene of serene beauty and quiet power, this tiny world actively venting its interior into space, the ice beneath your feet connected to an ocean kilometers below, an ocean that might harbor life, that might be home to microorganisms floating in the dark saltwater, feeding on hydrogen produced by water-rock reactions, completely independent of the sun, living in conditions we can barely imagine. Standing there, you would be standing at one of the most exciting places in the solar system, a place that represents one of our best chances of answering the age-old question, are we alone in the universe? Let that peaceful image carry you deeper into rest. The idea of Enceladus quietly orbiting Saturn, its geysers periodically erupting, its ocean sloshing gently beneath the ice, its bright surface reflecting sunlight across the Saturnian system. It's been doing this for who knows how long, perhaps billions of years, patiently waiting for us to discover it, to study it, to wonder about what it might tell us about life and the universe. And it will continue long after we're gone. This small, bright world, sparkling in the darkness, a testament to the beauty and mystery of the cosmos. Now let us visit a moon of fire rather than ice, a world so volcanically active that it makes Earth look geologically placid by comparison. This is Io, the innermost of Jupiter's 4 large Galilean moons, and without question the most geologically active body in the entire solar system. Io is slightly larger than our own moon, with a diameter of 3,643 kilometers. But where our moon is a dead, cratered world, Io is anything but. Io's surface is a riot of color, painted in shades of yellow, orange, red, black, and white, like some kind of cosmic pizza, as one scientist famously described it when the Voyager spacecraft sent back the first detailed images in 1979. These colors come from sulfur and sulfur compounds in various forms. Yellow areas are likely sulfur deposits. Orange and red areas are probably sulfur that's been altered by radiation or chemical reactions. White areas are sulfur dioxide frost. Black areas are recent lava flows, dark rock that hasn't yet been covered by sulfur deposits. Io has over 400 active volcanoes, more than any other body in the solar system. To put that in perspective, Earth has about 1,500 potentially active volcanoes, but at any given time, only a few dozen are actually erupting. Io, with a surface area about the size of Africa, has ongoing volcanic activity happening all over its surface simultaneously. Some of these volcanoes are so powerful that their plumes extend hundreds of kilometers into space, high enough to be visible from approaching spacecraft. Others produce vast lava flows that spread across the surface, covering hundreds or even thousands of square kilometers. The most powerful volcanic eruption ever observed in our solar system happened on Io in 2007. A volcano called Tvashtar-Katina erupted with a plume that reached 330 kilometers high. The eruption produced a curtain of fire, a fissure eruption where lava fountained from a crack in the ground rather than from a central vent. The lava fountain was about 60 kilometers long and fountained lava hundreds of meters into the air, or more accurately, into the vacuum of space, since Io has almost no atmosphere. This eruption released more energy than all of Earth's volcanoes combined release in an average year. Io's volcanism is driven entirely by tidal heating, but on a scale that makes Europa and Enceladus look tame. Io orbits Jupiter at a distance of only about 422,000 kilometers, much closer than Europa's 671,000 kilometers or Enceladus's distance from Saturn. Being so close to Jupiter means Io experiences tremendous tidal forces. Moreover, Io is in that same orbital resonance with Europa and Ganymede that affects Europa, the 4-to-2-to-1 resonance. This resonance keeps Io's orbit eccentric, and the changing tidal forces as Io moves closer to and farther from Jupiter generate enormous amounts of heat in Io's interior. Estimates suggest that tidal forces generate about 2 to 3 watts of heat per square meter of Io's surface, averaged across the entire moon. That might not sound like much, but integrated over Io's entire surface, it amounts to about 100 trillion watts, roughly equivalent to 100,000 nuclear power plants running continuously. This heat has to go somewhere, and it goes into melting rock and driving volcanic eruptions. Io's interior is probably mostly molten, with only a relatively thin solid crust floating on top of a vast magma ocean. Some models suggest that as much as 20% of Io's mass might be molten at any given time. The result of all this volcanic activity is that Io's surface is the youngest in the solar system. While ancient surfaces like those of the Moon or Callisto show craters dating back billions of years, Io has virtually no impact craters. Any crater that forms is quickly buried under volcanic deposits. The average age of Io's surface is estimated at only about 1 million years, and some regions are much younger, perhaps only a few years or decades old. Io is constantly resurfacing itself, burying its past under layer after layer of new volcanic material. Io's volcanoes come in several different types. Some are paterae, large volcanic depressions that can be over 100 kilometers across. These are thought to be volcanic calderas, formed when magma chambers beneath the surface empty out and the overlying rock collapses into the void. One of the largest, Loki Patera, is about 200 kilometers in diameter and is probably a lava lake, a depression filled with molten rock that's directly connected to Io's interior. Loki is one of the most powerful volcanic features in the solar system, regularly releasing more heat than all of Earth's volcanoes combined. Other volcanoes on Io are more traditional volcanic mountains, conical peaks built up by repeated eruptions. Some of these mountains are enormous. Busal Montes rises about 17 kilometers above the surrounding plains, taller than any mountain on Earth. These mountains seem paradoxical at first. If Io is constantly resurfacing itself with volcanic deposits, how can tall mountains persist? The answer seems to be that the mountains are formed by compression. The constant addition of volcanic material to Io's surface causes the crust to compress, buckling and thrusting upward to form mountains. They're not volcanic mountains in the traditional sense of being built by eruptions, but rather compressional mountains, similar to fold mountains on Earth like the Himalayas, except they're formed by crustal compression due to volcanic resurfacing rather than plate tectonics. Io's volcanic plumes are spectacular. Because Io has virtually no atmosphere, volcanic gases and ejected material don't encounter air resistance. They follow ballistic trajectories, arcing up from the volcano and falling back down to the surface in graceful parabolas. The plumes are often described as umbrella-shaped because of the way the material spreads out as it rises and then falls back. Different plumes have different heights and characteristics depending on the eruption's violence and the velocity at which material is ejected. Some plumes are relatively small, rising only a few tens of kilometers before falling back. Others are enormous. The Prometheus plume, first observed by Voyager and still active decades later, consistently rises about 70 to 100 kilometers. The Pele plume, another long-lived feature, reaches about 300 kilometers and has a reddish color, probably from sulfur that's been chemically altered in the intense radiation environment around Jupiter. The material from these plumes falls back to Io's surface over a wide area, creating halos or rings of deposited material that can be hundreds of kilometers across. Over time, these deposits change color as they're altered by radiation, creating the complex patterns of color we see on Io's surface. The lava on Io is hotter than any lava erupting on Earth today. Most terrestrial lava, basalt, erupts at temperatures around 1,100 to 1,200 degrees Celsius. But some of Io's lava flows have measured temperatures as high as 1,500 to 1,600 degrees Celsius. This suggests that Io's lava is not basalt but rather ultramafic lava, similar to the komatiite lavas that erupted on the early Earth about 3 billion years ago when Earth's interior was hotter. These ultramafic lavas are extremely hot and extremely fluid, able to flow rapidly across the surface and creating vast lava plains. One of the most striking features on Io is the variety of volcanic landforms. There are massive lava flows, some of which have been tracked changing over time as new eruptions add material. There are lava lakes, pools of molten rock contained within volcanic depressions. There are volcanic plumes actively erupting. There are recent flows that appear dark against the sulfur-covered plains. There are calderas, mountains, and mysterious features that scientists are still working to understand. It's a volcanic wonderland, a place where every type of volcanic activity we know of is happening simultaneously. Despite the constant volcanic activity, Io is not a hot world overall. Away from the volcanic hotspots, Io's surface is bitterly cold, around -160 degrees Celsius. The volcanic regions are hot, of course, but they make up only a small fraction of the total surface area. The rest of Io is frozen, covered in sulfur dioxide frost that's so cold it's hard. This creates a strange dichotomy. You could be standing on a plain of frozen sulfur dioxide, shivering in the bitter cold, and look across to see a volcano erupting with lava hot enough to melt steel, its plume rising into the black sky, glowing red against the darkness. Io's appearance changes noticeably over time. Comparing images taken decades apart shows that the patterns of color have shifted. Volcanoes have erupted and then gone dormant. New calderas have formed. It's one of the few solar system bodies where we can observe significant geological change on human timescales. A volcano that was erupting during the Voyager flybys in 1979 might be dormant when New Horizons flew past in 2007, while a new volcano has appeared somewhere else. Io is a dynamic, ever-changing world, perhaps the only solar system body besides Earth where a detailed map would need to be updated every few years to remain accurate. One of the most fascinating aspects of Io is how its volcanism affects the space environment around Jupiter. The volcanic plumes eject sulfur dioxide and other gases into space, and this material gets ionized by Jupiter's powerful magnetic field, creating a donut-shaped cloud of charged particles called the Io plasma torus. This torus orbits Jupiter at the same distance as Io, fed continuously by Io's volcanism. The plasma torus is enormous, extending about 200,000 kilometers from Jupiter's center and containing about a ton of material. The ions in the torus are accelerated by Jupiter's rotating magnetic field, creating intense radiation belts that make the Jovian environment one of the most hazardous in the solar system for spacecraft. The sulfur and oxygen ions from Io also bombard Jupiter's upper atmosphere, creating auroras, just as particles from the sun create auroras on Earth. But Jupiter's Io-induced auroras are more complex and more persistent than Earth's auroras, creating glowing ovals near Jupiter's poles that are always present. Io is essentially electrically connected to Jupiter through Jupiter's magnetic field, with a current of millions of amps flowing between Io and Jupiter's ionosphere. Looking at images of Io is both beautiful and unsettling. It's beautiful because of the colors and the variety of features. This world painted in yellows and reds and oranges, with black lava flows cutting across sulfur plains, white sulfur dioxide frost covering mountains, volcanic plumes visible as bright patches against the darker background. But it's also unsettling because it's so alien, so unlike anything we experience on Earth. This is a world of fire and ice existing side by side, where the ground beneath your feet might crack open to reveal molten rock, where volcanic plumes erupt with enough force to throw material hundreds of kilometers into space, where the very landscape shifts and changes beneath layer after layer of volcanic deposits. If you could stand on Io's surface, assuming you could find a safe spot away from active volcanoes, you would see a landscape unlike any other. The ground would be covered in sulfur and sulfur dioxide in various forms, crunchy frost in some places, slick ice in others, colorful sulfur deposits ranging from yellow to deep red. The horizon would be dotted with volcanic mountains, their peaks rising into the black sky. Perhaps somewhere in the distance, you would see the glow of an active volcano, its lava bright against the dim landscape. And overhead, dominating the sky, would be Jupiter, huge and striped with cloud bands, taking up about 20 degrees of sky, 40 times the apparent size of the moon as seen from Earth. Io is tidally locked to Jupiter, so Jupiter would hang in one spot in the sky, never rising or setting, slowly rotating through its 10-hour day. Io is often described as a hellish world, and from a human perspective, it certainly would be. The constant volcanism, the intense radiation from Jupiter, the bitter cold except near volcanoes, the lack of atmosphere, all of these factors make Io utterly inhospitable to life as we know it. But from another perspective, Io is magnificent, a world where planetary processes that take millions of years on Earth happen before your eyes, where the interior of a moon is quite literally on display at the surface, where nature's raw power is showcased in its most dramatic form. As you continue your journey towards sleep, let the fire and energy of Io fill your mind's eye. This is a world of constant change, constant renewal, where nothing stays the same, where the surface is perpetually being reborn. In its own way, that's comforting. It's a reminder that change is the only constant, that renewal is always possible, that even the most dramatic transformations are simply part of nature's eternal cycle. Io has been erupting for billions of years, will continue erupting for billions more, patiently reshaping itself over and over, never content to remain static, always in motion, always alive in the geological sense. Beyond the 4 large Galilean moons of Jupiter, there are many other fascinating satellites worth contemplating as you drift towards sleep. Ganymede, which we mentioned briefly, deserves more attention as the largest moon in the entire solar system. This giant world, bigger than Mercury, represents a middle ground between the icy outer moons and the rocky inner planets. Its surface tells a story of ancient violence preserved in dark, cratered highlands, interrupted by younger, grooved terrain where the crust pulled apart billions of years ago, allowing brighter ice to well up from below. Callisto, Jupiter's outermost large moon, is a testament to the passage of time. Its surface is perhaps the oldest in the solar system, covered with impact craters that date back 4 billion years or more. The largest of these is Valhalla, a multi-ring impact basin so vast that standing at its center, you would see concentric rings of ridges extending beyond the horizon in all directions. Callisto is dark, its ice mixed with rocky material and darkened by eons of radiation, giving it a somber, ancient appearance that speaks to billions of years of patient endurance. Neptune's largest moon, Triton, holds a special place in the pantheon of peculiar moons. It's the only large moon that orbits its planet backward, in retrograde motion, strong evidence that Triton didn't form where it is now but was captured from the Kuiper Belt billions of years ago. Triton is similar in size and composition to Pluto, and likely would have become a dwarf planet in its own right if it hadn't had the misfortune of wandering too close to Neptune's gravitational influence. Despite being so far from the Sun that temperatures plunged to -235 degrees Celsius, Triton shows surprising geological activity. The Voyager 2 spacecraft, during its 1989 flyby, discovered active geysers erupting from Triton's surface. These geysers erupt with nitrogen gas mixed with dark dust particles, shooting material up to 8 kilometers into Triton's thin atmosphere. The geysers are powered by solar heating, even though the Sun appears as little more than a bright star from Neptune's distance. Sunlight penetrates through a layer of translucent nitrogen ice, warming the ice beneath, which then sublimes directly from solid to gas, building up pressure until it breaks through in spectacular eruptions. Triton's surface is young and varied, showing different types of terrain that speak to complex geological processes. There's the cantaloupe terrain, so named because it looks like the skin of a cantaloupe melon, with irregular depressions and ridges covering large areas. There are smooth plains of nitrogen ice. There are regions where the surface has been broken and refrozen. The diversity suggests that Triton has been geologically active throughout much of its history, perhaps driven by tidal heating as its initially eccentric orbit gradually circularized after its capture by Neptune. But Triton's capture has sealed its doom. Its retrograde orbit means that tidal forces are causing Triton to slowly spiral inward toward Neptune rather than outward like most moons. In about 3.6 billion years, Triton will either collide with Neptune or, more likely, will cross inside Neptune's Roche limit and be torn apart by tidal forces. The debris from Triton's destruction will form a spectacular ring system around Neptune, probably more extensive than Saturn's current rings, though whether it will be as beautiful depends on the composition and structure of the debris. It's a reminder that even on cosmic timescales, nothing is permanent, everything is in motion, everything is slowly changing. Mars's 2 tiny moons, Phobos and Deimos, provide a contrast to the giant satellites of the outer planets. These are among the smallest moons in the solar system, irregularly shaped chunks of rock barely 22 and 12 kilometers across respectively. They're probably captured asteroids, leftovers from the asteroid belt that somehow got snared by Mars's gravity. Phobos is particularly interesting because it orbits Mars so quickly, taking only 7 hours and 39 minutes to complete one orbit. From the Martian surface, you could watch Phobos rise in the west, race across the sky, and set in the east about 4.5 hours later, only to rise again a few hours after that. Phobos is also doomed, slowly spiraling inward due to tidal forces at a rate of about 2 centimeters per year. In about 50 million years, it will either crash into Mars or be torn apart, creating a temporary ring around the red planet. The fact that we happen to live at a time when Phobos still exists is another reminder of how fortunate we are to be here now, able to observe and study these transient features of our solar system. Saturn's moon Mimas is famous primarily for one feature, the enormous impact crater Herschel. This crater is about 130 kilometers in diameter, roughly one-third the diameter of Mimas itself. The impact that created Herschel must have come very close to shattering Mimas entirely. The crater has a prominent central peak that rises about 6 kilometers above the crater floor, formed when rock rebounded after the initial impact compression. On the opposite side of Mimas from Herschel, the terrain shows evidence of stress fractures, probably caused by shock waves from the Herschel impact traveling through Mimas and converging on the opposite point. Despite the violence recorded in its surface, or perhaps because of it, Mimas has a peaceful quality. It's a survivor, a small moon that endured a catastrophic impact and held together, continuing its quiet orbit around Saturn as if nothing had happened. The resemblance of Herschel to the Death Star's superlaser dish is purely coincidental but has made Mimas one of the most recognizable moons in popular culture. Saturn's moon Miranda, orbiting Uranus, is one of the strangest-looking objects in the solar system. Miranda's surface is extraordinarily complex and varied for such a small moon, only about 470 kilometers in diameter. It has heavily cratered ancient terrain sitting right next to young, lightly cratered regions. Most strikingly, Miranda has several large ovoids, regions bounded by sharp boundaries where the terrain type changes dramatically. These ovoids show parallel ridges and valleys, suggesting some kind of tectonic deformation that's hard to explain for such a small, cold moon so far from the sun. The most dramatic feature on Miranda is Verona Rupes, a cliff that rises 5 to 10 kilometers high, possibly the tallest cliff in the solar system. Due to Miranda's very low gravity, only about 1% of Earth's, an object dropped from the top of this cliff would take about 12 minutes to fall to the bottom, reaching a terminal velocity of about 200 kilometers per hour. Of course, there's no atmosphere to create air resistance, so the fall would be in perfect vacuum, following a simple ballistic trajectory. Scientists have debated for decades how Miranda acquired such a varied and complex surface. The leading theory is that Miranda was once shattered by a massive impact that broke it into pieces. The pieces then reassembled under their mutual gravitational attraction, but not in their original configuration. Different pieces, with different geological histories and surface ages, ended up next to each other, creating the patchwork appearance we see today. It's a dramatic history for such a small, distant moon, a reminder that violence and disruption have shaped the solar system we observe today. In exploring the moons of our solar system, we've journeyed through a gallery of worlds that showcase the incredible diversity of planetary bodies. We've seen volcanic fire on Io, subsurface oceans on Europa, orange hazes on Titan, sparkling geysers on Enceladus. We've contemplated the ancient, cratered face of Callisto, the grooved terrain of Ganymede, the doomed orbit of Triton, the Death Star crater on Mimas. Each moon tells a story. Each contributes to our understanding of how planetary systems form and evolve. But beyond the scientific knowledge, beyond the geological details and orbital mechanics, There's something deeply moving about these moons. They remind us of the beauty and complexity of the universe. They show us that worlds come in varieties we never imagined, that nature's creativity extends far beyond the familiar landscapes of Earth. They inspire us with their strangeness and captivate us with their mysteries. The moons are also teachers. They teach us about patience. They've been orbiting their planets for billions of years, following the same paths, slowly evolving, gradually changing. Their timescales are geological, measured in millions and billions of years, reminding us that the processes shaping the cosmos unfold at their own pace, indifferent to human schedules and expectations. They teach us about interconnection. No moon exists in isolation. Each is connected to its planet by invisible threads of gravity, influenced by the sun's distant pull, affected by neighboring moons through orbital resonances and gravitational perturbations. The moons, planets, rings, and the sun form an integrated system where everything affects everything else, where changes in one part ripple through the whole. They teach us about resilience. Many moons have endured billions of years of bombardment, suffered catastrophic impacts, undergone tremendous tidal stresses, yet they persist, maintaining their orbits, continuing their existence. They've survived the solar system's violent youth and will likely survive for billions of years more, patient witnesses to the slow evolution of our cosmic neighborhood. And perhaps most importantly, the moons teach us humility. Looking at images of these distant worlds, realizing the scale and age of these systems, understanding our tiny place in this vast cosmic arrangement, it's hard not to feel humbled. We are newcomers to this ancient system, late arrivals on one small planet orbiting an average star. The moons were here long before us and will be here long after we're gone. Our concerns, which seem so large and overwhelming, are vanishingly small in the context of cosmic time and space. But there's comfort in that humility. It means our problems, however significant they seem, are temporary and limited in scope. The universe continues its patient unfolding regardless of our daily struggles. The moons continue their orbits. The tides continue their rhythm. The laws of physics continue to operate with perfect consistency. There's a kind of peace in recognizing that we're part of something much larger than ourselves, that we're embedded in a cosmos governed by understandable laws, that despite our troubles, the universe carries on its majestic way. The future of lunar exploration is bright. The coming decades will bring new missions to the ocean moons, new data about their interiors and surfaces, perhaps even the first detection of life beyond Earth. We'll continue to discover new moons as our telescopes improve. We'll develop better theories about how moons form and evolve. We might even, someday, send humans to explore these worlds directly, though that day is probably far in the future given the enormous distances and technical challenges involved. But even without physical exploration, the moons continue to serve their purpose. They orbit, they evolve, they exist as beautiful examples of nature's creativity. They're there for us to observe, study, and wonder about. They're there to remind us that the universe is full of marvels, that exploration and discovery are endless processes, that no matter how much we learn, there's always more to discover. Each moon is a world unto itself. Europa's ocean might be larger than all of Earth's oceans combined, yet it's completely hidden from view, accessible only through careful remote sensing and eventual exploration. Titan has weather, seasons, lakes, and rivers, an active methane cycle that mirrors Earth's water cycle. Yet it all happens at temperatures that would freeze carbon dioxide. Enceladus, tiny Enceladus, shoots geysers hundreds of kilometers into space, provides all the material for Saturn's E-ring, and might harbor an ecosystem in its subsurface ocean. Io erupts with such violence that it has covered its entire surface with fresh volcanic deposits in just the last few million years. These are not dead rocks. They're dynamic, evolving worlds, each with its own character, its own processes, its own story. They're as worthy of our attention and study as the planets themselves, perhaps more so because they're often more geologically active and potentially more habitable than the planets they orbit. As you move closer to sleep, feeling the weight of tiredness pulling you down, let your mind wander through these distant worlds one more time. Picture the moon, Earth's faithful companion, hanging in the sky just as it has for billions of years, its familiar face marked with ancient Maria and bright highlands. See Europa's cracked surface, its lineae crisscrossing the ice like roads on a map, hinting at the ocean below. Watch Titan's orange globe, its atmosphere thick and hazy, hiding a landscape of methane lakes and organic sand dunes. Marvel at Enceladus's geysers, delicate plumes of ice crystals catching the sunlight as they arc away from the South Pole. Witness Io's volcanic fireworks, lava fountaining from fissures, sulfur dioxide frost coating the cooling flows. See Ganymede's groove terrain, testament to ancient tectonic processes on an icy world. Observe Callisto's ancient face, cratered and dark, a record of billions of years of impacts. Notice Triton's geysers, powered by sunlight penetrating through nitrogen ice. Spot tiny Phobos racing across the Martian sky, rising in the west and setting in the east. Appreciate Mimas's enormous Herschel crater, survivor of an impact that nearly shattered the moon. Wonder at Miranda's bizarre patchwork surface, possibly reassembled after a catastrophic disruption. All of these worlds exist right now, at this very moment, orbiting their planets, following the laws of physics slowly evolving. While you sleep, Europa's ocean will slosh gently beneath its ice. Enceladus will erupt another few thousand tons of water into space. Io will erupt from another volcano. Titan's methane lakes will evaporate molecules into the atmosphere. The moon will tug on Earth's oceans, raising tides as it has for billions of years. These processes continue regardless of whether we observe them. The moons don't perform for our benefit. They simply exist, following their nature, shaped by gravity and energy and chemistry into the forms we observe. There's something profound about that independence, that autonomous existence. The universe doesn't need us to observe it to exist. It carries on with its processes, its transformations, its slow evolution, whether we watch or not. And yet, we do watch. We send spacecraft. We take images. We measure and analyze and try to understand. In doing so, we connect ourselves to these distant worlds. We extend our awareness beyond Earth, beyond our immediate surroundings, out into the solar system and beyond. We become, in a small way, citizens of the solar system, participants in a cosmic community of worlds. The moons await us. They orbit patiently, preserving their secrets, ready to reveal them to those who take the time to look carefully, to ask questions, to send sophisticated instruments across the vast distances that separate us. Each new discovery raises new questions. Each answer leads to deeper mysteries. This is the nature of exploration and science. The more we learn, the more we realize how much we don't know. But that's not frustrating. It's exciting. It means there's always more to discover, always new frontiers to explore, always new wonders to uncover. The moons will continue to surprise us for decades and centuries to come. We've only begun to explore them, only scratched the surface of understanding their complexity. Future generations will know things about these moons that we can only dream of now. Perhaps someday, humans will stand on the ice of Europa, drill down to the ocean, and lower a probe into the water to explore what lies beneath. Perhaps we'll fly through Titan's orange atmosphere, land on the shore of Kraken Mare, and sample the liquid methane, looking for exotic life. Perhaps we'll collect samples from Enceladus's geysers, bring them back to Earth, and analyze them for biosignatures with equipment far more sophisticated than anything we currently possess. These future explorations seem like science fiction now, but so did landing on the moon until we actually did it. So did sending rovers to Mars until we sent them. The impossible becomes possible through human ingenuity, persistence, and the drive to explore and understand. The moons beckon us onward, inviting us to visit, to study, to learn from them. But for now, for tonight, as you drift into sleep, it's enough to know they're there. To know that the universe is full of marvels. To know that beyond Earth's atmosphere, beyond the moon's orbit, beyond the asteroid belt, there are worlds of ice and fire, of oceans and volcanoes, of geysers and lakes, of ancient craters and young surfaces. To know that some of these worlds might harbor life, that we might not be alone, that the universe might be teeming with biology in forms we can't yet imagine. Let that knowledge fill you with peace. The moons have been there all along, will be there tomorrow and for billions of tomorrows after that. They're part of the stable structure of the solar system, part of the reliable order of the cosmos. In a world where so much seems uncertain and chaotic, the moons provide a reminder of constancy, of patterns that repeat, of processes that continue with patient reliability. As sleep finally takes you, as consciousness fades and dreams begin, carry with you the image of these worlds floating through space, bathed in the dim light of a distant sun, following their elliptical paths, slowly spinning, gracefully orbiting, eternally patient. They're out there right now, real places with landscapes and geology and chemistry, waiting for us to fully explore them, waiting to reveal their secrets, waiting to teach us more about the universe and our place in it. Sweet dreams of moons, of oceans hidden beneath ice, of methane lakes under orange skies, of geysers sparkling in sunlight, of volcanoes erupting in the darkness, of ancient craters preserving the history of the solar system, of gravitational dances between worlds, of the patient, persistent forces that shape our cosmic home. Let the moons guide you into peaceful sleep, these celestial companions, these worlds of wonder, these marvels of the solar system that remind us of the beauty and mystery and infinite fascination of the universe we inhabit. If you enjoyed learning about these incredible moons and their fascinating stories, please consider liking this video and subscribing to Deep Science Sleep for more relaxing science content to help you drift off to sleep. Rest well, dream of distant worlds, and know that the cosmos continues its ancient dance around you as you sleep. The moons await, patient and eternal, in the vast darkness of space.